Right, good afternoon. Welcome to the physics seminar. Today we are very pleased to have Don Wuebbles in Wichita. He is now retired professor at the University of Illinois, Urbana-Champaign. He spent 20 years at Lawrence Livermore National Lab doing atmospheric modeling over there early in his career, and then spent decades in Illinois continuing atmospheric modeling. And so today he's going to talk on evaluating potential impacts of aviation and rockets in the changing climate. Please help me to welcome Don Wuebbles.
Thank you. See if I can get this all set up here. And I feel like I'm way overdressed given what the weather's going to be here later today, but I may be shedding clothes as we go through this. So what I'm going to do is start out, and by the way, as emeritus professor, I'm really failing retirement, so I don't like people saying I'm retired because there's nothing retired about what I'm doing. I still have my research group. I still am advisor to the president of the university. I'm actually working full-time for a company on the side called Earth Knowledge. So I have lots of things going. And I'm still a major advisor to governments around the world, even if these days it's not our current government. So I'm going to give you a little bit of overview to start on climate change because it kind of sets up the rest of the talk. And then I'm going to talk about studies we've been doing recently, primarily looking at supersonic transports because they're come back again. I'll touch on current aviation along the way though. And then I'm going to end up by talking about the impacts of rockets. So you just get a little bit of an introduction to some of these things we're doing. So first of all, it's important to realize that we've already seen over 1.2 degrees. It's actually probably closer to 1.3 or so right now. Over the next 3 or 4 years, we're going to pass 1.5 degrees centigrade globally, which was one of the marks set by the Paris Agreement as what we want to achieve. So we're going to skip way past that. We're probably going to skip past 2 degrees over the next couple of decades. 2024 was the warmest year in record. On the very top is the temperature record from NOAA, showing that temperature didn't change a whole lot during the 1800s. Early 1900s, we saw a little bit of an increase. And then over the last 50, 60 years, we've seen a huge increase, such that the temperature changes we're seeing now have not been seen before in human history. So 2024 was the warmest year in record. It was a El Nino year. 2025, a La Nina year, was tied basically with another La Nina year in 2023. 2020, then 2016. The last 11 years have basically been the warmest years on record. And in every decade for the last 5 decades has been warmer than the previous, and setting the record for the warmest decade on record. So we're seeing something very unusual in human history. And as they said in Pogo, we found the enemy, and it is us. So if we go back 2,000 years, which is the bottom graph, using paleo data for climate change, you can see very small changes happening during that time, yet you can see the medieval maximum when Vikings were living in Greenland. You can see the Little Ice Age when it was very cold in North America and Europe, and reflected in many paintings in Europe. And then you look at the current temperature, which is the red, and you see that current temperatures are way above anything we've seen since the time of Christ, globally. This is annual average, globally averaged temperatures. To give you more of a feeling, this is the temperature we have now compared to the last million years or so. Last few million years. To see the kind of temperature changes that we will see by 2050, you have to go back about 3 million years ago. By 2100, there's some uncertainty in that because it depends on what we choose to do between now and then in terms of human-related emissions, but we could be far higher than anything certainly than anything humans have seen in the 700,000 years or so that humans have been on the planet. But still not used to this. So how does all this happen? Well, the main driver of the changes we've seen are the emissions of gases and particles related to human activities, either by fossil fuel burning, which is the primary source, or through land use change, which is also important, non-negligible. And the reason this is important is because what's called the greenhouse effect. Greenhouse effect was discovered by Joseph Fourier, very famous physicist and mathematician. Fourier effect, Fourier transform, Fourier series, etc. In 1824, he proposed the greenhouse effect, where solar radiation, which comes in ultraviolet and visible wavelengths, comes into the Earth's atmosphere. About 30% of that gets reflected to space from clouds and ice on the Earth, ice and snow, and the rest is absorbed. Because of the temperature of our planet, it's re-emitted in the infrared wavelengths. And if that radiation went to space, this would be a frozen planet. It'd be too cold to have life as we know it. But because of certain gases called greenhouse gases, the single most important one, which is water vapor, it has a very short lifetime, and so therefore we treat that as a feedback within the climate mechanisms. The real driver of the change that we're seeing is carbon dioxide and methane, but those gases are also important in the background atmosphere as well. And so we have temperature as we know it. It's like having a blanket over the Earth's surface and allows life as we know it. What we're doing by increasing the amount of carbon dioxide, the amount of methane, the amount of nitrous oxide, and some other gases and particles is we're like adding an extra blanket. So going back to Fourier, the reason that was then substantiated initially by some laboratory studies done by Eunice Foote, an American scientist who was never given credit because she was a woman. And we didn't give women credit for science. So John Tyndall, an Irishman working in England, got all the credit. But now in the last few decades, we started to give Eunice her credit that she deserved. All of that work has now been substantiated by many other studies, including satellites, that show that the greenhouse effect works as we said it would. So that takes us into what's called radiative forcing. The increase in the driving of increasing energy in the atmosphere is largely becoming because of the amount of carbon dioxide increase, but also these other gases and some particles. And also some feedbacks within the mechanism, within the chemistry of the atmosphere affecting ozone, for example, that affect the forcing on climate. So you end up with a total anthropogenic forcing of about 2.7 watts per meter squared. And that results in the temperature change we've seen at this point. But the atmosphere is also in imbalance. The energy of the system's is not in balance. And it has, of course, like any physics mechanism, it wants to go back into balance, and that's going to cause even larger temperature changes just from the emissions we've had already. And we're continuing to emit lots of carbon dioxide and these other gases, so we're continuing to grow the problem. So many lines of evidence demonstrate that human activities, especially these emissions of greenhouse gases, are responsible for this observed climate change. For the period extending over the last century, there are no credible alternative explanations. You will see in the media that, oh, it's just the sun, you see, it's just cycles. Neither works. There are no such cycles that can explain this large change. There are important cycles in the Earth system. You understand most of those, if not all of those. And we know it's not the sun because we've been measuring the sun from satellites in great detail for well over 50 years now. And the sun has actually decreased in output, not increased. So the sun can't explain the observed temperature record, the black line there. Only when you bring in these greenhouse gases and particles can you explain the observed temperature record. I'm skipping over things very quickly. So I want to get into aviation and rockets. So subsonic and supersonic aircraft can directly emit, burn basic aviation fuel, kerosene. Emits carbon dioxide into the atmosphere and other important gases. The heat of the engines produces nitrogen oxides in the atmosphere, breaks the N2 into nitrogen oxides, emits water vapor, and some particles, soot, and if it has sulfur in the fuel, sulfate, into the upper atmosphere and lower stratosphere. And I am getting warm, so I'm going to try to get rid of my coat. Particularly warm in this room. So rockets on the other hand, probably don't even need this in this small room. So we're going to talk about three different types of rocket fuel are likely to be the choices for the future. Solid rockets, today, often used today, are not likely to be the rocket fuel of the future. They do emit some chlorine, they emit some aluminum, they can create particles, and they have some small effects, but we don't think that's going to be what you're going to be seeing over if we go to two-stage rockets over the next, multiple stage rockets over the next 30 years. So we're going to choose some that were picked out for us by a leading rocket expert from Aerospace Preparation and look at those. So emissions from aviation and rockets can both affect the ozone layer, and we'll talk a little bit about the ozone layer. Ozone is really important to us because it absorbs ultraviolet radiation, keeps the most harmful ultraviolet radiation from reaching the life on Earth, and so the ozone layer is relevant. And when we're looking at climate impacts, particularly in terms of looking at the radiative forcing. And it depends what those emissions are as we look at things. I'm going to start out by looking at aviation. So when we use, when you go through a jet engine, you have emissions of carbon dioxide, about 2%, 2 to 2.5% of current emissions of greenhouse gases comes from aviation. So aviation right now is kind of a minor player in the overall emissions of carbon dioxide, but not an unimportant one. We emit water vapor, get nitrogen oxides, as I mentioned already. We get some unburned hydrocarbons, a little bit of CO. Those don't have a huge impact. Some soot and some sulfates because there's sulfur in the fuel. And all those can have an impact. There's been a number of analyses looking at the current emissions and their effects. So this is very similar to the other one. The graph I showed you looking at the effects of all the greenhouse gases emitted and particles being emitted on climate. This is for aviation only. And basically says we got a couple important things. One is the emissions of carbon dioxide. There is an effect on ozone that we need to be concerned about, but it's kind of minor. And because current aviation spends most of its time in the upper troposphere, we can find supersaturated layers of water vapor. We form contrails, and contrails are a big concern right now. Lots of people concerned about contrails. I think a lot of that concern is going to evaporate because there's new studies suggesting that where we form contrail cirrus clouds in the upper troposphere, that instead of contrails leading the way in forming contrail cirrus, that most of that cirrus would have formed anyway where the contrails happen to be emitting. So that you may adding much smaller amounts to cirrus than previously thought from contrails. So I'm leading a special report for ICAO, the International Civil Aviation Organization, UN body that oversees aviation around the world right now, and with 30 other scientists working with me. And I think one of our big conclusions is going to be that contrails are maybe not quite as important as these results would imply, which if you look at the bottom, the non-CO2 terms are not negligible, but the biggest one of all of those is contrails, and particularly the contrail cirrus. Now, there's various factors affecting aviation's climate impacts. I've already mentioned most of those, but it's important to recognize the lifetime of these gases and particles. CO2 has a first e-folding time, first lifetime, is about 100 years. Its second e-folding time is over 1,000 years because it doesn't just decay in the atmosphere, it has to be removed to the deep ocean and then taken slowly out of the Earth system. Nitrogen oxides only last for a few weeks. Water vapor, similar in how it's removed. It's in the troposphere, it's like 9 days or less. Stratosphere, it's somewhat longer. Ozone, 1 to 2 years in terms of the effects of changes on it. Methane has a lifetime of 10 to 12 years, so you have to worry about any methane that might be emitted. Particles, weeks to maybe a month or so. Contrails, 2 to 3 hours, but can last for days, up to a week or so, again, depending on whether you form contrail cirrus. CO2 effects are very well understood. Nitrogen oxide effects, pretty well understood as well. Particles have effects that we don't totally understand because they also affect clouds. And we have a pretty good idea what impact they have. So there remains significant uncertainties. And there's really major uncertainties about contrails, except these new observations are suggesting that maybe we've been overestimating contrails. Currently, there are about 25,600 commercial aircraft. And that's a few years ago, so maybe out of date. In 2023, airlines worldwide carried around 9 billion passengers, transported 60 million tons of freight on 40 million commercial flights. Every day, aircraft transport over 10 million passengers and around 18 billion US dollars worth of goods. By the mid-2030s, no fewer than 200,000 flights per day are expected all over the world. And the demand for air transport is expected to increase by an average of 3 to 4% per annum over the next 20 years. 4% was the last update. I think they may be slowing down slightly based on some analysis. Today, I'm going to mostly talk about supersonic transports because that's what my new study is. We've been looking at supersonic transports for boom and various proposed aircraft. I'm going to show you a hypothetical study based on an aircraft that was designed by MIT. So these are aircraft that fly at greater than 1 Mach, and Mach number greater than 1. Particular one we're going to look at is Mach 1.6. The Concorde was about 2. And these would fly in the lower stratosphere, basically. Most of the flight time would be in the lower stratosphere. The question is, with the sonic boom, are they going to have to fly in at subsonic speeds in the troposphere part of the time? Some of the analysis we've done have looked at it both ways. And it does have an impact because it affects how much time you're spending in the stratosphere. But most studies still assume that we're not going to be flying at supersonic speeds in the troposphere, even though there have been some statements from the Trump administration suggesting that they would allow supersonic flights over land. We'll see how the public accepts that, if that were to be the case. So So there are new commercial aircraft being under consideration. Boom continues to develop their aircraft. For a while, there was lots of consideration of business jets. Gulfstream and some other companies were talking about supersonic business jets. That's kind of collapsed. I haven't even heard much about it. There were several companies talking about mid-size and larger. Several of those companies already went out of business or dropped developing such aircraft. Boom is kind of the one remaining one that I know of that is continuing to design an aircraft that would be about 100 passengers, roughly. And the aircraft we're going to look at today is pretty similar, not exactly the same as theirs. I didn't want to show their study because they have the rights to it. I don't. Or the study I did for them. So we still need to understand the impacts of these aircraft, and particularly fleets of these aircraft, and the potential noise issues, which I'm not really going to get into today. And there's many factors that go into this. The design of the aircraft, the fleet size, the characteristics, what city pairs you're going to assume. The Mach speed, of course, because that affects how high you're flying. The cruise altitude, the fleet fuel burn at cruise. So, what are the engines like, and how much emissions are they going to make? What are the nitrogen oxide emissions, which are not directly related to fuel burn, because it depends. You can design an aircraft to have low nitrogen oxide emissions if you want to, and the type of fuel that's going to be used. I will not talk too much today about sustainable aviation fuel, but I think that is the future, and we will be transitioning slowly to that over the next 30 years. And that is, rather than using a fossil fuel source, uses plant-based or related kind of biologically related sources for the fuel. So we're going to look at the resulting impact of assumed fleet on ozone and climate. Won't get too much in air quality today. These are somewhat smaller aircraft, so they don't have a huge impact on local air quality, but it's something that other people, we need to look at and we'll be looking at. Now, just to give you a feeling for these aircraft, they're going to be flying in the very lower stratosphere, 10 to the Mach number, of course. The ozone layer peaks around 25-kilometer altitude. 90% of the ozone is in the stratosphere, what we call good ozone, because it protects us from ultraviolet. About 10% is in the troposphere where we live. We call that bad ozone because you don't want to breathe it. But the model considers ozone everywhere. So if you look at the emissions of nitrogen oxides, we're concerned about those emissions in the stratosphere because nitrogen oxide emissions plus ozone gives you NO2. The NO2 will react with an oxygen atom, which is produced from ozone photolysis. And essentially, you're destroying two ozones when you go through that sequence. And you have a catalytic reaction because you get the nitrogen oxide back again. And so you can keep doing this many, many times until you remove the nitric oxide as either nitric acid or some other molecule, less reactive molecule. Similarly, for the hydrogen oxides, water vapor gets oxidized into OH, and you can go through a sequence that also destroys ozone. The importance of these different catalytic mechanisms depends what altitude the emissions occur at. That's going to be ever more important when we look at the rocket study than it is for the aircraft, because here we're just emitting into the very lower stratosphere. Rockets emit at all altitudes. So we did some parametric studies on SST fleets about 5 years ago that were published, not the fleet I'm going to show you today, but a fleet that was commonly used by NASA in the early 2000s. And what it showed is there's a sensitivity to the nitrogen oxide emissions, as you might expect. Larger nitrogen oxide emissions, the less ozone. You get a decrease in ozone. Actually, at very low nitrogen oxide emissions, you can produce ozone because of the complexity of the chemistry involved. Altitude is also important, so the Mach number is important. And so as you go up in altitude, you get larger decreases in ozone. The nitrogen oxides have that much larger impact. Nitrogen oxides and hydrogen oxides. But particularly in nitrogen oxides. So those effects really do depend on the particular aircraft. So I don't have a nice picture graphic of the aircraft we're going to talk about. So this is actually a plane that was designed by Georgia Tech University. A little bit flies a little higher, Mach 2.2, and had 55 passengers. The one we're going to look at is Mach 1.6 and has 100 passengers. But the actual kind of design of the aircraft is probably pretty similar because all these aircraft, the boom wing looks very similar to this, actually, in its design. But you know how big the fuselage is in terms of how many passengers and all these kind of things are different. And also the strength of the engines to take it higher Mach speed. So the particular design, we're going to look primarily at the high scenario, which assumes about 1,000 aircraft. They said flying at Mach 1.6, 100 passengers, range about 3,500 miles. Fuel burn total is 7.15. I'm not sure what kilograms per 100 sea miles or sea kilometers. Total fuel burn about 43 teragrams. And then we assumed a nitrogen oxide emissions that are kind of typical of today. It's not assuming a really low emission for nitrogen oxides. And I don't think we assume sulfur as being in the fuel in this aircraft. So this is the city pairs. So most of it occurs in North America and Europe, and so heavily in the Northern Hemisphere. But there are plenty of flights still in the Southern Hemisphere as well in this. The lower scenario just assumes less aircraft and that you're going to burn a lot less fuel. Less interesting because it produces very little effect, because once you bring down the aircraft by a factor of 6 or so, you're not having much of an impact. But also, economically, it may not make sense to have that few aircraft. That's one of the big problems with SSTs all along, is the economics. And you probably have to have in the order of 1,000 aircraft to make it economically really feasible. It shows the fuel burn distribution. Most of the emissions occurring where you're assuming cruise is in the lower stratosphere, but also, in this case, over land, subsonic, bringing down into the troposphere. And then the distribution, as I mentioned already, is heavily oriented towards which is the graph on the right, oriented towards the Northern Hemisphere. We're going to use our whole atmosphere climate model, demonstrated climate model that developed by friends of mine at NCLAR. And so it's complete representation of atmospheric chemistry and physics. It derives the atmosphere from scratch. And then we use the output, or use the an output for a typical year from that to then run the dynamics. So we don't have to, so we can separate the signal from the noise more readily by using constant dynamics for a year. It's about 1 degree latitude model for 200 gases, 500 reactions or so, and runs on a supercomputer. It's very slow, usually a couple of days per year of model time. We need to run about 12 years to get a change in ozone, or change in the atmosphere sufficient to look at everything. So we're going to start with looking at the effects on ozone. So the total ozone changes are over the entire year at steady state with this 1,000 aircraft. You're seeing global ozone change reduction of about 0.3%, much smaller than the changes we've already seen from chlorofluorocarbons, which peaked at about 6%. But not negligible in terms of the effect. Maximum ozone reduction with altitude is about 1% at a given altitude. And the northern hemisphere is just under 1%, much less, of course, in the southern hemisphere. This shows the distribution of the changes in ozone for the two cases, the MIT high and low. And what we see is actually a net increase in ozone in the troposphere. The nitrogen oxides produce ozone in the troposphere. They destroy ozone in the stratosphere. And so it's this. So when we're looking at the total change, it's looking at that balance. And yet we're really concerned about what's happening in the stratosphere because of this concern about ultraviolet radiation. Plus, it has an effect on climate. And so the total column doesn't tell you the entire story. You want to, even though 90% of the ozone in the stratosphere, 10% in the troposphere, there's still this balance that happens, counterbalance in terms of the total column. Most of the change is spread out for the stratosphere. Most of the changes in the northern hemisphere spread out more in the troposphere because the air in the troposphere gets more well mixed more readily. Now turning to the radiative forcing on climate. So that ozone change has an effect on climate. And for the high case, we're talking about 20 milliwatts per meter squared. So remember I showed you the initial, what we've seen already from human activities is about 2.7 watts per meter squared. So this aircraft would add about 20 milliwatts from ozone. Then he added a water vapor direct effect because it also has a direct greenhouse effect. The bicarbon causes a slight cooling effect. Sulfates would cause a cooling effect. And the net total is on the order of 15 milliwatts per meter squared. You need to add in the amount of CO2, but the CO2 has a long lifetime. It really depends how many years you're going to use this aircraft. And so you can get on another you can get something comparable in size in terms of milliwatts from that amount of CO2 over the next 30 years. And so that also needs to be considered in doing this. So this is assuming fossil fuel-based jet fuel. We'll talk a little bit about SAF in a minute, sustainable aviation fuel. So this is not a large impact, but it's a non-negligible impact as well. So the question is, would you allow these aircraft based on their environmental impact? Probably, but you might kind of want to watch carefully over what impact they are having. So in summary, the radiative forcing driven by carbon dioxide, ozone, water vapor, and so forth are important. And the stratospheric radiative effects would persist due to the slow transport to the troposphere. Troposphere is well mixed all the time and gases coming in and out quickly. Not so much in the stratosphere, which has a lifetime in the order of a couple of years. So there are small but non-negligible effects on the radiative forcing compared to other ongoing human factors that I mentioned already. And the conclusions is that proposed SST fleets, while likely, may not be economically feasible, but if they are economically feasible, this could be in our future. A lot of people would love to fly a lot faster across the world. And so we'll see what happens. But the effect on the ozone layer is very, very small. The effect of 1,000 aircraft. The effect on climate are also quite small. Less than 0.03 degree centigrade climate change if I take that radiative forcing and turn it into a climate change temperature. And then there's all those factors that I mentioned before that really determine what the ultimate effect will be. The new kid on the block, a lot of work going on, is development of sustainable aviation fuel. The aim of the Federal Aviation Administration is that over the next 30 years that they convert entirely to sustainable aviation fuel. They don't know how to do that yet because it's not so simple making enough fuel to satisfy the worldwide needs. ICAO's projections are similar. They're aiming at the same thing. If we did sustainable aviation fuel, which means you use a plant or some artificial means of developing the aviation fuel, chemical might be slightly different than the current, but similar. And so it would burn in current engines. But you wouldn't have CO2 emissions because those CO2 emissions are already taken care of by the fact that you grew a plant which drew CO2 from the atmosphere in the first place to get this carbon into the fuel. And but the nitrogen oxide emissions remain pretty similar to now. You won't have the same mix of hydrocarbons, very little soot, likely, maybe more organic carbon. Probably the characteristics of when they do fly in the troposphere, less overall contrails than would be projected otherwise. But a lot more work needs to be done to understand sustainable aviation fuel. So I've already been kind of through all of these conclusions, so I'm going to pass over those quickly for time's sake. But it's important to realize that as real designs for fleets of SSTs are developed. Now, we've looked at the prototype for Boom, but will that prototype change a lot? Certainly the engine would change a lot, I think, in the coming years. That needs, all these things need to be looked at more clearly, along with the noise impacts. And we have the tools to do this, but we also need observation. Let's turn to rockets. Just process of submitting this paper to journal right now. And so there's been recent strong growth in the space industry, which is expected to continue to grow over the coming decades. Most of these words are coming from our colleague at Aerospace Corporation, who worked with us on this, Marty Ross. And the spacecraft use continues to evolve unpredictably, making it difficult to know how fuels or rocket designs will evolve over the coming decades. What we did in this study is choose 3 potential scenarios where it is assumed one propellant has become the primary fuel for all rocket launches. In reality, it probably end up being some kind of mix, but it could be that one of these dominates, or it could be something we're not expecting. As I mentioned earlier, solid rockets are probably not the winner. They probably fall off by the wayside for various reasons that I admittedly don't fully understand. So we chose RP1, which is very much like kerosene, methane, and H2 as representing, so methane and hydrogen as the potential fuels. RP1 accounts for approximately 85% of current rocket launches and could remain a major propellant in the future. Methane and hydrogen are considered strong candidates for future rockets, but how it really will go is unclear. The launch vehicle concept used to calculate the ascent trajectories and generate profiles of propellant mass is 2-stage heavy lift vehicles carrying 4,800 tons of propellant, delivering 75 tons to a 200-kilometer orbit. And the propellants used by 2050 is assumed to be distributed among 5,000 rockets. Currently about 300 launches per year, so it's expected to increase rapidly. The graph on the bottom shows the altitude distribution of the emissions. And you can see where this goes from first stage to second stage. And the change in emissions from extensive emissions in the troposphere and lower stratosphere to much less emissions until you get way up in the upper atmosphere. So RP1, high thrust, long missions, emits carbon dioxide, black carbon, nitrogen oxides, some water vapor, lots of water vapor, expendable and reusable rockets, both. Methane is efficient, reusable rockets. Um, lower emissions overall, easier to store. Hydrogen, highest efficiency, zero CO2 and black carbon, but puts out a lot of water vapor. It's lightweight and is ideal for reuse, expecting that most rockets in the future are going to be reused rockets. Oops. The graph on the right just basically shows the corresponding emissions that large CO2 emissions from RP1 and methane, water vapor emissions from all three, but particularly from hydrogen, and then many other emission types that are treated in the model. But black carbon is one, particularly from RP1, that you don't get nearly as much of from the other sources, the other fuels. This shows where we assume spaceports would be for the future, and kind of the size of the circle is how many launches per year. So the biggest launch site is considered to be in Florida at that time still, but with growing entities in China and elsewhere. These weren't selected by me. Again, Marty played a big role in choosing these locations. Resulting impacts on ozone. So we get the largest impact on ozone. So looking at the left side, upper left. So that's for RP1. We get the largest impacts in the tropics from all those 5,000 launches at all those different sites. The smallest changes globally at the poles, with an increase in the poles, a decrease in the tropics in total ozone. Return to methane, it's a small decrease almost everywhere, but particularly in the tropics. Slight increase in the polar regions. And then with methane, or with hydrogen, putting in all that water vapor just ends up with a decrease everywhere. And I'll try to explain a little bit more of the chemistry as we go look at the ozone line. So this shows the altitude distribution of the changes in ozone for the three different choices. So in all cases, we end up with an increase in ozone in the troposphere. The nitrogen oxides and water vapor are added to the troposphere and the lower stratosphere. Lower stratosphere is largely controlled by water vapor and nitrogen oxide. So if you add more water vapor, you're going to get you're going to get getting a slight increase in ozone. Above that, you get a decrease in ozone because the water vapor's helping you. So what's happening with the water vapor emissions happening in the troposphere and lower stratosphere, it's actually interfering with processes that would destroy ozone, like the nitrogen cycle. Produce more nitric acid instead of having to go through that catalytic reaction. So you end up producing ozone in effect. And above that, in the upper stratosphere and the mesosphere, you end up destroying ozone because that water vapor is eating up the ozone through the ozone catalytic cycle. And so we end up with this dichotomy. So it isn't, again, it's not good enough just to look at the total column. You really need to look at the change with altitude, because that ends up determining the climate impact. Larger impact with RP1, a little bit smaller with methane, and very little effect on the stratosphere with hydrogen. Most of that effect ends up being in the troposphere, lower stratosphere. So common patterns is ozone increase in lower to middle latitude stratosphere, ozone increase in the upper summer polar regions at high latitudes, main changes occurring below the stratopause, about below 50 kilometers, a decrease in the mesosphere, but it's much smaller, a lot less ozone up there as well. And you do see the differences between the three choices of fuel. Let me turn to the climate effect and look at the radiative forcing. The largest radiative forcing, looking at the total, and that's again not including the CO2 effect, comes from RT1. Hydrogen has the smallest forcing. It has smaller effects on ozone. Water vapor effects are smaller overall, and no carbon dioxide and no black carbon. The black carbon coming primarily from RT1 and methane. And then adding in CO2 would add about 1.75 watts, milliwatts per meter squared for RP1, 1.56 for methane, assuming 30 years of time frame that you're going to continue to burn, do these launches at the same level. So, so it would be somewhat larger than the number on the right side here. But again, you're talking about a pretty small overall impact, but non-negligible. If you controlled everything else, you might want to start getting concerned about this. We switch all other energy and transportation to renewables, then you start worrying about these kind of sources. So in summary, we evaluate the environmental impact of 500 rocket launches per year across 3 different fuel types. The type of fuel does play a major role in determining the effects on ozone and climate. All fuels examined produce ozone increases in the lower to middle stratosphere and decreased ozone in mesosphere and above, upper stratosphere and mesosphere and above. Both conventional RP1 and methane fuels result in decreased total ozone levels in the tropics and increases towards the poles, while H2 fuel produces a decrease everywhere. Radiative forcing effects on climate are in the milliwatts per meter squared, very small for this study, assumed scenarios relative to the current forcing on climate from human activities. And I thank you. This, by the way, is a graph based on photograph from space, how thin the atmosphere is.
We have time for questions, of course.
Yes.
Re-entry of satellite would be similar effect as the rocket.
We proposed to FAA that we would continue the study with the idea that we would look at re-entry this year, and they canceled the study. Yes.
Thinking of the ozone depletion scenario that was discovered in the 80s with the
Chlorofluorocarbons.
Harvest.
Started in 1974. Right.
Examine green emission. What effect that part of the
I worked with Moline and Roland on a number of papers in the early 70s where we looked at the effect of chlorine. So I've been a leader in looking at chlorine and bromine effects on the atmosphere for 50 years. So we haven't looked at rocket. We haven't looked at the rockets. The primary concern there is the solid fuel, which we decided to skip by. I thought we would do that early on, and then Marty suggested no, he didn't think they're going anywhere. So we decided that that's not going to end up being the key fuel of the future. It would have an impact if we were to have lots of chlorine emissions, of course, and so we'd be very concerned about that. Yes.
What is the takeaway from the station? Should I be should acknowledge that the rainfall and it should be like this? The second thing is it more like socio-economical and political kind of mindset that we have scientific evidence, we have a study, but frontier is keeping on terrible. So is it more about we are lacking data, we are lacking our efforts to make our environment normal this, or is it more like ideological that we are not able to get it?
So that's a mixture of questions. First of all, takeaways. Takeaways is that both cases, if we had a fleet of supersonic transport, or if we have 1,000 rocket or 5,000 rocket emissions, you might want to be of concern, but you don't need to have immediate concerns about policy, and you can kind of look at how this develops and maybe develop even better technology over the next 20, 30 years that help reduce those effects. So, but you need to be aware that these impacts are non-negligible. Politically, the science of climate change is well known. For the White House to call it a hoax is just ridiculous. You know, calling it a hoax is a hoax. There's no basis for that. So it's a choice to say that we think burning fossil fuels is more important than impacts on people. That's a choice. I don't think it's a particularly good choice, but that's the current choice. Yes. We're past the halfway point, I think, and you know, all indications are it's going to be a lot more difficult in the future. Why? But you make a lot of money in the near term if you just keep supporting this idiotic policy. Yeah. Many energy companies are already heavily invested in alternative energy fuels, so they're well aware. They're just making a lot of money from fossil fuels. Yeah, so you exactly. That's why I'm here.
Yeah.
That's why I came today, actually. You know, I had no reason to come to Wichita other than the guys, I wanted to tell you guys about what's really happening in the world. And he wanted to hear about aviation and rockets because that's a big concern around him. Yeah. Yeah. This is what we do as scientists. Economics is still a big question. My friends at Boeing are not designing an SST, even though they've designed several prototypes in the past, because they still don't think it's economically feasible. Yeah. People at Boom are very positive that they think this will work. Whether they're right or not, I don't know. Yeah, don't make too much of that, because that same week the atmospheric conditions were such that we probably would not have had many contrails anyway. So it's not a good week to have that have had happened, but that's what happened. It depends on supersaturated layers, very small supersaturated layers in the atmosphere that is where contrails form. And we just didn't have, and the analyses since show, well, we didn't have many supersaturated layers that week. It just happens. You know, some weeks we have lots and some weeks we don't. Yeah, and we can't say that had a real impact because hmm, yeah. I think the public's interest in aviation continues to grow. So therefore, I don't think that will happen. Yes.
recommendations as far as resources to find current facts and updates about what's going on?
Yeah, we still try to feed plenty of information to the media, but one good source is an NGO called Climate Central. It tries to report on the latest understanding of the science. A lot of good friends there. Nature Conservancy is putting out more on climate than they have in the past. Environmental Defense Fund as well. Union of Concerned Scientists still tends to put out some info. But I particularly like Climate Central. And there's a couple other NGOs that also put out a fair amount, but I like that one particularly. Yeah. Oh, I'm sorry, someone back there.
One, climate impact and how that include let's say carbon emission because of the storage, because hydrogen and methane storing at high limit.
It's assumed there will be no emissions from that cryogening. Yeah. So yeah, it's yeah, you're right. I mean, if there were emissions from that, then you'd have another concern. Yes.
Talk about mainstream media not carrying the news on this so much, but what about mainstream media outside of the U.S., like BBC?
Yeah, they still have a lot. I developed a reputation for my 2 years at the White House with President Obama that I put out a daily, almost daily, email about what's kind of climate disasters are happening around the world. You know, what's happening with climate change around the world. And so I would put out bullets of like 3 or 4 items every day. Which when I met President Obama, he said, "Oh, you're the guy that sends me all this things about how bad the world's getting." But I continued to do that. And it used to be, I could still get a fair amount of information out of the New York Times and Washington Post and a few other places. But it's a little harder to get information because a lot of those climate or science news desks have been closed down around the country, as media is in general having more and more problems. But around the world, The Guardian in the UK is almost a daily source of information on what's happening with climate. And there's many other places as well.
Well, the airports is coming up with things. You know, we're all driving hybrids right now, electric cars. So too are propulsion systems that take off on a cleaner type fuel or electric, get or hybridized, get to altitude, and then you can really back off on fuel consumption. The supersonic transports, however, have in your calculations, did you consider takeoff and landings for those emissions?
They were, but we did not look at the local airport effect, which is where you would primarily see those effects. There are other analyses of those, and they're very dirty because they have to take off at pretty high energy. But we did not look at the local air quality effect. We were looking at the global effects.
So you basically said at the beginning that we are going to fly past 1.5 degrees, flunk on 2 degrees and keep going. What could we do? What would be most impactful to slow down the warming?
The most important thing we can do is to reduce emissions from energy and transportation, convert our energy and transportation to renewables. Because that's where most of the source of CO2 comes from. Land use change is not unimportant. And as you look at future land use change, that has to be considered. But particularly that's, things like burning down the rainforest and things like that. There are other.
So don't consume foods with palm oil. All right. And electrify everything. Okay.
Well, or have other, there's lots of other alternatives besides electrifying everything, but I do think we're going to move heavily away from centralized power to more distributed power, and that's just the way of the future. Even if we use nuclear as part of the solution, which I think is part of the solution, it's likely to be small nuclear plants, and those are still under consideration, and even potentially using them in industry. But how that develops is still unclear.
For the record, I do not believe in those as part of the solution, but we'll see.
It may have a short term.
I've always looked at it as an interim. I didn't show in this side. I think what we're going to do is we're going to shoot well past 2 degrees. We'll decide that this is so bad for humanity that we're going to start doing something, and the emissions are going to peak out, and then we're going to say, oh, it's very expensive to remove CO2 from the atmosphere, but maybe we'll have some new techniques over the next 30, 40 years, and we'll start removing CO2 from the atmosphere to get us back down below 2 degrees or 1.5, whatever it is we say is the goal. So this overshoot idea is what most scientists are now looking at, because they think we're going to be at an overshoot phase before people catch on and say, oh my God, we got to be doing something. When New York's underwater, maybe we'll understand.
Yeah.
Might add, one of the airlines, I forgot which one it was, has started a plant in Liberal, Kansas to build fuel, jet fuel.
Oh, for SAF.
I think.
Yeah. Yeah, there's a whole number of different plants being under consideration.
Trading water for the.
Yeah, exactly. Yeah, exactly. I'm not sure Kansas is probably the best place, because you're using underground water in that case, and you already got a problem with the Ogo.
Well, all right. I don't see any other arms raised. So let's thank Don one more time, and we can always continue this.